for including me in this session. I'm Yaoxuan Zeng from Peking University, and my advisor is Jun Yang. Today's topic is wind-driven ocean circulation on tidally locked aqua-planets. And I want to focus on two main features of the ocean circulation on these kind of planets: ocean superrotation and the equatorial vertical motion. First, let me introduce the research background of our experiments. When we search for life beyond the solar system, we mainly focus on the planets in the habitable zone around M dwarfs because we have found several planet systems like the TRAPPIST-1 system. And because the habitable zone around M dwarfs are very close to the star, so the planets will easily get tidally locked due to the strong tidal force. As a result, the one side of the planet will permanently face the star, and the other side will get no radiative heating at all. So as a result, the climate on the planets will likely to be an IBO mode. So the open ocean area will be constricted in the day side around the substellar point. However, if we take ocean heat transport into consideration, the open ocean area will be largely expanded because ocean can transport heat from the substellar point to higher latitudes and to the night side. And we call it lobster mode because it is like a lobster with two claws here and a long tail to the night side. And this is very significant for the habitability of a planet because with ocean heat transport, it can warm the night side, and thus it can protect the atmosphere from condensing down on the night side. And it can also restrict the thickness of the ice from thousands of meters if we don't take ocean heat transport that can grow that thick to the order of tens of meters, so that the water will not freeze at the night side, so that the liquid water will be trapped on the night side to ices. Former researchers have found this phenomenon, and our work is mainly to show the inner mechanism of the circulation and give a clear picture of it. So we carried out our experiment on Earth-like aqua-planets with ocean depths of around 1,000 kilometers. The model we use is the CCSM3 all-coupling model with active ocean, land, and sea ice dynamics. Because we are simulating an aqua-planets tidally locked around M dwarf, so we did some change in the spectrum and the rotation period. And next is the main part of our speech. The most important feature of tidally locked aqua-planets is the ocean superrotation. This animation shows the ocean surface zonal velocity. We can see that at low latitudes, the ocean current is uniformly eastward, and it can reach about 1 meter per second. We know that it's quite large. The ocean superrotation not only just exists at the surface of the ocean. In fact, it can reach until the bottom of the ocean in our experiment. So we want to figure out what makes this kind of superrotation. Because the ocean current is mainly wind-driven, so we want to have a look at the wind stress. The wind stress is shown here. It is convergence to the substellar point, as well as two hot spots due to the ocean heat transport. And we can also notice that the wind stress on the west side is stronger than the east side. So if we calculate the zonal mean results, we'll find that the wind stress, the red line, is also eastward at low latitudes. So we may get the conclusion that the ocean superrotation is mainly driven by the atmosphere superrotation. However, our story is not that simple, because we can see there are some differences between the atmosphere and the ocean. In the atmosphere, there are two jets, while in the ocean there is only one jet. So there must be some inner adjustment within the ocean. In order to answer this question, we did more careful analysis on the momentum budget using the zonal mean time averaged zonal momentum equation. And we divided the advection terms into mean circulation, stationary eddy, and the transient eddy moment transport. As a result, we can find although the wind stress is not very strong at the equator, the stationary eddies, the purple line, is very strong at the equator, and it can compensate for the wind stress. And we can see that the sum of them reaches the maximum at the equator. So the stationary eddy transport is very important because it changes from the atmosphere's 2 jets into the only 1 jet at the equator of the ocean. And this is all about the surface ocean superrotation. And let's move to the next part of the equatorial vertical velocity. We know that the vertical velocity is also very important to the biology because when there is upwelling area, there will be a mixing of the ocean and the nutrients will be transported from the bottom of the ocean to upper levels. And we focus on the equatorial area because the most significant features is at the equator. And the most important feature is that there is a downwelling area to the east side and an upwelling area on the east side. And this can be explained by the Ekman transport. Because we know that the wind stress is convergent to the substellar point. So the Ekman transport near the equator will be like this way. So it will converge on the west side and diverge on the east side. And this convergence and divergence will cause the downwelling area and the upwelling area. However, we also find that the momentum transport is very important to the downwelling area. We know that the downwelling is caused by the convergence of the water, and we can divide the convergence into x direction and y direction. The Ekman transport is mainly contributed to the y direction, but we can find that the x direction convergence, the blue line, has a large contribution to the downwelling. So what causes this kind of zonal convergence? We found that it is the eddy momentum transport. This figure shows the momentum transport from higher latitudes to the equator, and it reaches the maximum at around 100 degrees east. So this kind of momentum transport will cause also the zonal velocity to reach maximum here. And because the zonal velocity is maximum here, so it will cause a convergence east of it and thus contribute to the downwelling area. Now we have a basic picture of the ocean circulation on tidally locked aqua-planets. First, we can observe that there exists atmosphere superrotation as well as ocean superrotation. And they have some differences with 2 jets in the atmosphere and 1 jet in the ocean. This can be explained by the eddy momentum transport, which is dominated by the stationary eddies. And we have this kind of wind stress and momentum transport, and we will get the vertical motion of the ocean near equator to be a downwelling area on the east side and upwelling area on the east side. And this not only occurs at this experiment, it actually occurs in different conditions experiments for the tidally locked aqua-planets, so it's more widely applied. And that's all for my presentation. And some other things is that we notice that the equatorial superrotation is not strongest at the surface, but at deeper in the ocean. And this is caused by the thermal wind relationship, and it is the same as what we know the equatorial undercurrent that occurs on Earth's Pacific. And that's all. Thank you.
Have a couple minutes for questions.
Yeah, Charlie Lineweaver from the Australian National University. I got the impression that you were modeling tidally locked rocky planets in the habitable zones of M dwarfs. Is that right?
Yes, but actually, it's rocky planets with ocean of around 1,000 meters, and we have no land distribution on these planets.
All right, and does the things that your results, do they depend very strongly on how close this thing is to the host star? For example, there's the inside of the habitable zone, the outside of the habitable zone. It's semi-wide.
Okay, this is the planets that in the middle range of the habitable zone.
And do you think it would change depending on if you got a little closer or got a little further out?
Yes, and another paper from my advisor Jun Yang in this about maybe February 2019 points out that if we put the planets to the inner edge of the habitable zone, then the temperature gradient will be weaker, so the wind stress will also be weaker, and the ocean current will be weaker. And in the inner edge of the habitable zone, the ocean heat transport will not be so important, and the atmosphere's atmosphere's heat transport will be more important.
And on the outer edge, is it the reverse?
And the outer edge, we haven't done much about the research.
Thank you.
I think.
Hey, nice talk, Tad Kamasic, University of Chicago. So you showed that the horizontal eddy momentum transport leads to superrotation, but does the vertical eddy momentum transport also reinforce superrotation?
Actually, with this results is an vertical integrated and average, because we want to wipe out these two terms. And actually, if we just calculate the this momentum budget in different layers, the vertical momentum transport has a large influence. But we know that when it is integrated vertically, this will just be zero. So we think that the ocean superrotation can reach the whole depth of the ocean. So we focus on the horizontal terms.
I think we'll move on. Thanks. Let's thank our speaker again.
Thank you.